So the input of the digital modulation is time discrete data, for example this. And this data should be modulated onto an analog carrier, which is for sinusoidal signal, and it is altered in a way so that it in the end carries the data. But how can this be achieved? So we have time discrete digital data and we want to modulate it onto an analog carrier. So the question is, how can we achieve this? To modulate the data, we take a step in between. So the data is transformed or converted to the time continuous domain again. So we introduce the concept of symbols. You know that the analog carrier is a time continuous signal, and the step in between is that we transform the data to some kind of time continuous signal too. But in this case, the signal is also value discrete. And the first data symbol here is 3. So we started with 3. And we retain this value for a certain period. And this period is called the symbol period. And each symbol is has the same symbol period. So the next value is 0. So our value drops to 0. And this value is also retained for the whole symbol period. Next one is 2. And 1. And then 3 again. And each symbol here is t-sim long. Yeah, so what's actually behind those symbols is a rectangle function. The rectangle function is formally defined by this equation here, and each symbol is a rectangle function which is shifted in time here. So n is the symbol index, and the value at n is given here, and here is the rectangle function. And this is the formal definition of the symbol stream, which is a time continuous signal. And this time continuous signal can then be taken to modulate an analog carrier. So what you see here is a theoretical approach to represent the data. So the data is here represented by numbers, and these numbers are plotted over time. But there are different representations of data. So we need a symbol mapping which maps the data to a symbol. And this symbol then some kind of converted to other representations, which can be then given to the modulator. For example, if you imagine that here is the boundary between the digital and the analog domain, and the modulator works solely in the analog domain, then each symbol, for example, can represent a voltage. But in the modulation techniques which we consider here, the modulator is mostly implemented in the digital domain. So there's some kind of digital circuit which does the modulation, and then here is an analog to digital converter, and then the RF front end follows, and it generates the high frequency signal, which can then be transmitted over the air or over a wire. But however, the actual implementation is not important here. What you need to know is that there is some data, and the data on the computer is binary data. So there are bits, 1 and 0s, or high and low, or high and low. And there are different representations to denote binary data. So what's important here is that this binary data stream is then is mapped to symbols, to discrete symbols. And below there's an example which maps 2 bits to 4 discrete symbols. Yeah, so this is also just an example representation, so you can also name symbols different, like A, B, C, D, or something else. But that's also not important here. What's important is that the symbol is a discrete value. And now we take 2 bits, and to each combination of the 2 bits, a symbol is assigned. Yeah, for example, there's a data stream like this. Then this data stream is divided into chunks of 2 bits, and a symbol is then assigned. Yeah, so what's important here is the notation. So this is the least significant bit, and here is the most significant bit. Whereas in this notation, yeah, it's 2. Yeah. So then we can look up the next chunk, which is 2. And then it's 1 and 3. So our symbol mapping gave this symbol stream from this input data stream. And now these symbols can be fed into the modulator, and the modulator generates a signal which can then be shifted up to the RF band. On the receiver side, the inverse process is done. So there is a demodulator here, which gets the signal from the RF front end. So it's, for example, a down-converted signal. And the demodulator then extracts the symbols from the input signal. And what's important here is that the decoded symbols are noisy. Yeah, so on the way from the sender to the receiver, the signal is subject to noise. and this noise is also present after demodulation. And this noisy signal must then be assigned to data. Yeah, so here there are symbols, and now we want to reconstruct the data, which can then be processed by a computer. And the data detection has to deal with the noisy signal. So here is an example where we have two symbols, 0 and 1. And yeah, so the data detector just puts this red line here in the middle between the two symbols, and everything that is below this red line is 0, and everything above the red line is a 1. So this this input symbol stream would decode to the symbols 0, 0, 1, 1, and now these symbols must be mapped to data again. So actually what is done is the inverse function of this assignment here. But as we have only two symbols, we can easily map this to the data. Or maybe just to make it clear that we use symbols here and not data, let's rename this two symbols. Yeah. So this is an inverse mapping. We get the data here. Okay. And in the next diagram, there's a different situation. So in the above diagram, the signal to noise ratio was good, and here we have a poor signal to noise ratio, so there's a lot of noise compared to the signal power. And now you see the problem. Basically there's the same function behind this symbol stream here, which is the output of the demodulator, but due to the noise, the first symbol can, for example, be decoded to B, and the next is an A, which is correct, and here it's a B, it's correct too. And the last one is an A again, which is false. And now we do the inverse mapping. This becomes this data stream. So you see that there is a lot of errors here in the decoded data stream. So this is an error, and no, this is not an error, but the last one is an error here. And this is just because of the poor signal to noise ratio. And this error can be measured. It's the here it's the bit error rate, BER, bit error rate, and here the bit error rate is 50%, whereas the signal above is decoded correctly, so there is no bit error here. A digital communication system has to deal with those bit errors, because you cannot avoid them completely. There's always noise in the system, and there will be bit errors. The poorer the signal-to-noise ratio is, the more bit errors are present after decoding. And in the later videos, in the later lectures, we will consider coding theory, and this coding theory is the basis of detecting those bit errors, and it's even possible to correct them. But for now, we just accept that there are bit errors